Hello, Royals. To supplement the examples on lesson 5.0, I want to develop a couple of other equivalent trig ratios. Now, there are students that get frustrated with this lesson because they feel like they should be able to see the answer. These are not, we are building identities here, but it's not new identities that you have to memorize. These are things that you should be able to illustrate and explain. And that's really how we're going to approach the question. Very much like most of our questions in Unit 4, we're going to use the sketch and we're going to use the definition. Okay. So, like, I understand when students can't see the process 7 steps from now, but to say, well, I don't know how to start here, I think would be silly. We're asked to find an expression on an angle in standard position, theta, in quadrant 1, that's equivalent to the sine of theta plus 3 pi by 2. So, we're going to start by sketching theta in quadrant 1. I think the frustration comes in because we don't know exactly what theta is going to be, but that's actually like that's the whole point to this, is that it doesn't matter where theta is. It does matter how you draw it, though. I don't want you to draw it assuming that it's going to be pi by 6, or draw it assuming that, like, drawing it so that it looks like pi by 4 would be problematic because we're going to lose the representation. Maybe I'll do this at least twice here to convince you that it doesn't matter how you draw it. But if you give me the choice of how to draw theta, I would try to draw it so that I could tell the difference between my x value and my y value. So let's draw and label theta in quadrant 1 first, and go ahead and assume or set the coordinates of a point on the terminal arm. Not saying, oh, I'm going to assume that this is right 4 up 1. No, just that it's right A up B on a circle of, let's say, radius C. So really what I'm doing is I'm going to set x to be A, y to be B, and r to be C. Okay? The next thing you want to do is figure out where the given angle is going to be. In this case, if theta is there, we should be able to figure out with a high level of precision where theta plus 3 pi by 2 is going to be. Sketch, in this specific case, the thing that we want to do is sketch theta plus 3 pi by 2. So in class, or in the printed lesson, we did, that's where theta plus pi by 2 would be. We did in the lesson or in class, that's where theta plus pi would be. This right here is theta plus pi by 2, 2 pi by 2, 3 pi by 2. It would be, its terminal arm would be right down there, wouldn't it? There's no memorization here. You should be able to figure that out. There's a couple of ways of seeing this, actually. I saw it as, give me a sec, theta plus 3 pi by 2. I saw it as theta plus a pi by 2, 2 pi by 2, 3 pi by 2. You might see it, and it might be valuable to see it, as a pi by 2, 2 pi by 2, 3 pi by 2 plus a theta. Because knowing that this angle is the same as that angle right there may be valuable. Okay. Well, let's talk about these triangles in a little bit more detail, or the ratios and the coordinates in a little bit more detail. Might have been nicer if I had drawn a better circle. Okay. We can think of there as being triangles here, but let's not forget that we want to find coordinates. So notice, first off, that these two radii are equal. Radius 1 is equal to radius 2. That's given. We're on the same circle. Okay. Theta 1 is equal to theta 2. Also given. You can do that just with arithmetic. If this is theta plus 3 pi by 2 and you subtract 3 pi by 2, you'll be left with theta. And then you have another angle in here. You have, I don't know what to call it. Normally I would call it, maybe I call it angle C1. Angle C1 is equal to angle C2. Also observed, there's a right angle triangle in there. That's kind of given. Okay, Now, if we have two angles the same and two triangles, that means that the triangles are similar. But if we also have a shared side length, that means that these triangles are congruent. We have proven congruence. I hope you had a chance to prove similarity and congruence in grade 10. Because of that, we know that the side lengths are the same. What's different, though, is the directions. And this is where having a diagram that's drawn in a decent manner here is going to help you. You see that distance of A? Doesn't it look like that distance should be the same? But I'm not worried about distances when I'm using XYR definitions. I want to know coordinates. If this point is over A, to the right A, then this point is going to be down A. And if this point is up B, this point right here is going to be right B. Okay? I guess up here we could have said that for theta, we're going to set x to be A, y to be B, and r to be C. And that means that, because we've proven congruence, for theta plus 3 pi by 2, x is going to be B, y is going to be negative A, and r is, of course, still C. Notice none of this depended on what ratio we were given. In fact, we can do all sorts of examples here like we did in the printed lesson or in class. We can find an expression for the cosine of theta plus 3 pi by 2, for the cotangent of theta plus 3 pi by 2, whatever we want. Okay, let's concentrate on the sine here. I know that the sine of theta is going to be theta's y divided by theta's r. The sine of theta is b over c. I wonder what the sine of theta plus 3 pi by 2 is going to be. I shouldn't be wondering, I shouldn't be guessing. I can read it off of my diagram. The ratio of y to r is going to be, whoops. Okay, so it turns out this wasn't useful. That's all right. The sine of theta is going to be, the sine of theta plus 3 pi by 2 is going to be the ratio of its y value to its r value, negative a to c. Here, let's squeeze that in there, up there. Let's pull this negative out front here. So ignore that. Where have I seen the ratio of a to c before? Well, the ratio of a to c would have been the ratio of x to r for theta. So if I just leave that negative out there, I notice that this is theta's x to theta's r. It's not the theta plus 3 pi by 2's y. No, it's theta's x. The ratio of x to r for theta would have been the cosine of theta. So what we have proven here, and it's not likely going to be a valuable identity for you, is if theta is in the first quadrant, then the sine of theta plus 3 pi by 2 is going to be equal to the opposite of the cosine of theta. Okay. We have determined a ratio on theta that is kind of equivalent to, or it's an operation on a ratio that's equivalent to the sine of theta plus 3 pi by 2. Okay, you draw your diagram and you use your definitions to discover the relationship. You shouldn't be remembering much at all here. Maybe congruence. Here, let's try another one with this. Let's do, I don't know, can I squeeze it in here? I think if I just scroll up there, we should be able to find it. How about, I don't know, the cotangent of theta plus 3 pi by 2. Well, the cotangent of theta plus 3 pi by 2 is going to be theta plus 3 pi by 2's x to its y value. Its x to its y value is going to be b to negative a. I don't like that negative in the denominator there. I might not want to put it out top, though. Let's put it out front. And I get negative b to a. And then I'm going to concentrate on b to a. And I'm going to try to find a ratio on theta that's going to measure b to a. Well, the ratio of b to a on theta would be the ratio of y to x. I recognize the ratio of y to x Let's get the negative out of the way. It's out of the way now. The ratio of b to a is theta's ratio of y to x, and theta's ratio of y to x is called the tangent of theta. Now, I did not know that this was going to be the right answer. I had not prepared this question, but I just discovered with you that the cotangent of theta plus 3 pi by 2, as long as theta is in the first quadrant, some of these properties won't work out exactly the same if you're in a different quadrant. But if theta is in the first quadrant, the cotangent of theta plus 3 pi by 2 is going to be the opposite of the tangent of theta. Okay, I'm not going to put a box around that because it's not an identity that I'm ever going to find useful, and I definitely don't want to try to memorize it. But I can figure it out from diagrams. Okay. I mean, we can recycle this diagram if we wanted to just try one other example. I don't know, let's do like a secant ratio. Here, we'll redraw a new diagram, and I'll place the angle in a different spot. Let's try, what did I say, secant? Secant of theta minus pi by 2. You're going to recognize pretty quick that the diagram is almost going to be identical because of my choice of operation here. But I just wanted to have a different operation than what we did in class. So I am going to sketch a theta. This time I'm going to make theta maybe a little bit bigger than pi by 4. But I'm still going to put it in the first quadrant. Maybe to get over the A's and B's, let's call it, I don't know, C comma D. Here's theta. Let's set for theta. Let's set x to be C, y to be D, and r to be E, I guess. So you sketch your angle, you set a point and a radius. I said I would try to find a nicer circle. That's not going to work. All right, we're doing it freehand again. Which is not going to work out great. Kind of egg-shaped. Yeah, well, it's not going to get much better. Okay, now let's figure out where theta minus pi by 2 would be. You could think of it as negative pi by 2 plus theta. I kind of see it as theta, and then let's go clockwise, pi by 2. Let's make it look perpendicular, maybe turning my ruler, lining up my terminal arm on that 8 line there will help me draw it a little bit more accurately, because precision here can help you make the correct predictions. Okay, so this should be the same C. Here is theta minus pi by 2. Right there. Theta minus pi by 2. That's actually, sorry, that right there is theta minus pi by 2. Okay. Now we have a side shared and an angle shared. And if we look right here, this is actually theta's complement, the pi by 2 minus theta. So we have another angle shared. So we have congruence. And that means for theta minus pi by 2, let's see here. Looks like I'm going right D instead, but then down C. So x is going to be D, y is going to be negative C, and my radius is still E. Okay. Now we go to our definition, the secant of theta minus pi by 2. If you want to put in like your ratio here, let's see, secant reciprocal of cosine. This is going to be the r from theta minus pi by 2 divided by the x from theta minus pi by 2. Like using XYR definitions is great. You just want to make sure that you're on the correct angle right here. So that's going to be my r value, C, over my x value, D. And notice I don't need to deal with the negatives like I did up above here. I just ask myself, where have I seen the ratio C to D before? Wait a minute, that's not right. R value. Oh, it's because I changed my radius, didn't I? That's an E. And because my E's look like C's, or C's look like E's. Yeah, anyways, yeah, I recognize this as being theta's R value divided by theta's Y value. So that's R from theta divided by Y from theta. And the ratio of R to Y, that's the reciprocal of the reciprocal of a sine ratio is going to be the cosecant ratio. There's no opposite here. There's no negative in this case, because why would there be? I didn't stumble upon any negatives. So we just proved that if theta is in the first quadrant, the secant of theta minus pi by 2 is going to be the same as the cosecant of theta. Okay. On quizzes or tests, you will likely be given expressions or ratios that you have not seen before. So having any of this memorized is not going to be helpful. What you should, let's say, remember or understand what to do is you draw a sketch and you use your definition. And those strategies should not sound new. It should be pretty ingrained in us by now. Try it out.